Let's look at a different example. So for the sake of illustration, I've increased the cost between x and z to 50. And now everyone starts with a different set of initial distance vectors. Now eventually, after running the distance vector protocol, we would see the tables converge as such. Let's suppose that the cost of the link between x and y suddenly increased from 1 to 60. Well, now in this case, y would need to update its view of the shortest path between y and x. Now it's no longer 1, but it's not 60 either. To see y, let's go back to our Bellman-Ford equation. We can see that y thinks it can get to z with a cost of 2, and that z can get to x with a cost of 3. So in fact, it's going to update this entry from 1 to 5. Then it will tell its neighbor, z, its new distance vector. In other words, that now its distance to x is no longer 1, but 5. At this point, z needs to recompute its shortest path to x. Now it knows that it can get to y with a cost of 2, but it thinks still that y can get to x with a cost of 5. Therefore, this entry is no longer 3, but 7. And now z sends its new distance vector back to y. Y then updates its distance vector for z, and this process continues. So then y thinks it is now 9 units away from x. So z has to do this all over again, and now z thinks that its shortest path is 2 plus 9, or 11. Now this process repeats, of course, until z finally realizes that it has a shorter path of 50 directly through x, after this counting up process exceeds the value of 50. This problem is called the count to infinity problem, and the solution is called Poisson reverse. The idea here is that if y must route through z to get to x in its table, as it did here, then y advertises an infinite cost for the destination x to z. So instead of sending 502, y would send infinity 02. This would thus prevent z from routing back through y, and immediately it would choose the shortest path to x of path cost 50.